In this video about mathematical induction, we will learn a whole new proof method, which will be very often used in this lecture. Proof by induction. So, what is the aim? The aim is now to introduce a new method for proving statements of a certain form, namely for proving statements of the form A of n, so it's just some statement making a claim about some n, where n is a natural number. So some equation or inequality or something involving some parameter from n. And we will see some examples later in this section, but this is the kind of idea that we want to introduce. And this, the way this proof method works, we will first formally derive, similar to what we did in the previous section about the natural numbers. Namely, this is called the induction principle. Namely, assume we have a subset of the natural numbers called M, which has two simple properties. First of all, 1 is contained in this set. Second, for all n in n, we know that if n is an element of M, so this is the statement that follows, if n is an element of M, then n plus 1 is an element of M. Oops, sorry, I hope it's still readable. So it follows that if n is in there, then n plus 1 is in there. Then it follows that m is already equal to n. And this is kind of heuristically, you can really see what's happening here. We know 1 is in the set, and by the second condition, if 1 is in the set, then 2 is in the set. And if 2 is in the set, then by using this condition again, 3 is in the set, then 4 is in the set, and so on, and so on, and so on. It's like a, if you take a big number, an infinite number of domino tiles, and put them all in a line, so that if you tip the first one, they all will fall down. This is basically what's happening. So it's kind of, we are proving that if we tip the first domino, so if the one is in the set, and if we know that the dominoes are put in such a way close to each other that if one falls down, then the next falls down, they will all fall down. So this is the same systematics that we're using here. So think of this infinite line of domino tiles in a certain way. Okay, this just formally can be very quickly proven, namely by 1 and 2. M is an inductive set, just by definition of inductive sets. So an inductive subset of R. But by definition of n, as this, with this property of inductive subsets, we know that n is contained in every inductive subset. Of R. Since this holds the case, it follows that n is a subset of M. But by definition, M is a subset of n, so the other inclusion also holds. And this means that both sets are equal. Okay, what does this have to do with proving statements? This is now a corollary of this theorem. So that corollary, this also gets a number, 158. So we take A of n to be a logical proposition about n in n. So the setting that we want to study here. So if the following conditions hold, first of all, A of 1 is a true statement. So inserting 1 for this natural parameter, we get a true statement. Secondly, we know that if an is true, for some n that we know, for some n in n, then it follows that a of n plus 1 is true. So if we can show these two things, so this is just assuming that for one particular n, we have that this statement is true, and derive out of this assumption that a of n plus 1 is also true. This is again this domino falling here. If this is the case, then a of n is true for every n in n. So then we have really proven that this statement is a true statement for every n. So this is just a consequence now of this induction principle. Because the proof is very simple, we just need to apply apply theorem 157 to a particular set, namely to the set M is defined to be the set of all n in n, for which a of n is true. And then we immediately get that, so if 1 is in there, so it means a of 1 is true, and if this domino mechanism works, so which is the second part in here, then we get that this M has to be all of n. Okay, so the strategy of proof by induction, I can now outline this, so how can we use this to prove results? The strategy for proof by induction, we will see examples immediately afterwards. So, what do we want? We want to show the statement a of n for all n in n. So then we use the following steps. The first part is called the base case. Namely, we show that the statement is true if we insert 1. So show that a of 1 is true. And usually this is the simple part of the proof, because this becomes usually a very simple statement, as we will see in some examples. Secondly, this is not really a step of proof, but a part that's very important, the so-called induction hypothesis. Assume that a of n holds for some, not necessarily for anything, but just we have some n for which this is true. Holds for some n in n. So if we have this base case and if we make this assumption here, this hypothesis, then there's the third crucial step, and this is now the domino mechanism, the so-called induction step. Show that a of n plus 1 is true, assuming the induction hypothesis. So assuming the induction hypothesis holds true. Okay, so this is now the method of proof we can use to really show results. And yeah, maybe I erase the blackboard to have more space for the examples so I don't have to interrupt in the middle. So let me just erase, and then we will see certain examples of this method. As a first example, I want to discuss some properties of the natural numbers that I haven't technically discussed here with this new definition. And they can be proven using the induction principle. So, let m and n be natural numbers, then the following properties hold. First of all, the sum of m and n is again in n. This seems quite obvious, but technically we have introduced n as the strange subset of the real numbers. This hasn't been shown yet. Secondly, m times n is again in n. Thirdly, every natural number is bigger than or equal to 1. And finally, if m is the smaller of the two, so if m is smaller than n, then n minus m is again a natural number. Something that's also non-obvious. And we will only prove part A of this. The proof is not very difficult if you know how to use the induction principle, and the other three parts can be kind of shown in the very same way. And I really encourage you to kind of think about these proofs, and maybe you could find also prove a part of it yourself. And so this is kind of a good way to learn about induction. So proof of part A. Namely, how can you do this with induction? We consider m as a fixed number. So we fix some number m, and then see this m plus n in n as a statement about this variable n, where n is a natural number, and then do induction over n. So prove by induction over n. And now it's important to keep really the steps in the induction. So if you write down the induction proof yourself, as you will have to do in some of the exercises, you have to follow basically the same scheme so it becomes clear what happens and which steps you're taking. So first of all, we have to study the base case. This is just the case n equal to 1. So this is very easy. Since m is an element of n and n is inductive, so, let me maybe add this in a small box. So here, the statement a of n that we want to prove here in this, just to add this formalism here, would be that m plus n in n. That's just some statement about n, right? So, as a base case, sorry. The base case would be now that n is equal to 1. Let me just add this for the first time. Okay, and now we know that since m is a natural number and n is inductive, it follows from the definition of inductive sets that n plus 1 is again a natural number. So this is the proof, m plus 1 is again a natural number. So this is the proof of the base case. This is just very, very simple. So the induction hypothesis is now that a of n holds for some n, so that m plus 1 in n is true for some certain n. And we need to derive the induction step from this hypothesis. So induction step. So we assume the induction hypothesis. So we first assume that m plus n is element n for some n in n. So assume we know a number n such that this is indeed true. Since the addition is associative, and this is all we need here, it follows that, so what we need to show? We need to show that m plus n plus 1 is again a natural number. But the associativity gives us that this is the same as m plus n plus 1. So this is the same as this. Since m plus n is a natural number by induction hypothesis, and again, n is inductive, it follows that this is plus 1 is again in n. And this completes the proof. So it follows that this is an n, and this is what we wanted to show. This completes the induction step. And this was our first, first induction. So if we have these cases here, let me maybe add this as a concluding sentence. So from these two arguments, it follows that m plus n is a natural number for all n in n. Okay, and the other parts of this theorem are proven in a similar way. Okay, we want to do some less abstract statements, so a bit more, where it becomes a bit more clearer how this induction procedure works, and so some more concrete examples. To do so, I want to introduce some notation that will be used basically all the time throughout the semester. And this is just shorthand notation for some things we already know. A, if we are in a field, if K is a field, and we have A1, A2, and so on until n elements of K. Comma. Then we define the sum, and this is the capital sigma if we talk about Greek letters. This is the summation sign in mathematics. Namely, we can write this as this term, and I will explain this in a moment. This is just the sum of all these n things. A1 plus A2 plus ... plus AN, if we sum them all up. And this just means we have the sum of all elements AI, where A is some number which starts with 1 and goes until n. So the sum over AI from 1 to n, or yeah, the sum over from I equal to 1 up to n of AI. So this is from the summation sign. And this is what you really have to get used to, because we will use this all the time. So this is, of course, again, an element of K. This is just the sum of elements of a field. So this is some standard notation for sums. Then something more concrete I also want to introduce. For n in n, we define a number called n schräg, and this number is called n factorial. In German, it's n Fakultät. I have no idea why the strange name here, but n factorial, and this number is defined as the following. You just take n times n minus 1 times n minus 2, and so on, and multiply all the numbers until we reach 2 times 1. And this is, again, a natural number by the previous theorem, part B. So the product of natural numbers is, again, a natural number. So the product of all natural numbers from 1 to n. Okay, and sorry, put 0 schräg. This we just define as 1. This is what we will need for technical reasons at some point. Okay, so first maybe some example about how to write such a sum. This is example 161. If we write the sum of the odd numbers 1 plus 3 plus 5 plus and so on until the odd number 2n minus 3 plus 2n minus 1. So add all the odd numbers up to this number. This is up to this 2n minus 1. This can be computed as the sum of I from 1 to n over 2i minus 1. If I is equal to 1, this becomes 1. If I is equal to 2, we get 4 minus 1, which gives 3, and so on, and so on, and so on. And so we can write this in this nice, concise notation. Okay, so now we come to a very famous equation, which has a nice story. Namely, this theorem is also called the little Gauss, by the famous mathematician Carl Friedrich Gauss, who was one of the most important mathematicians of all time, I guess. And it's kind of an interesting story. Namely, the theorem goes as follows. The story goes as follows. When Gauss was still a little boy and he was in school, he was obviously very good in math, and so he was always done the first with all the math stuff, and then doing all kind of mischief he wasn't supposed to do. So since his teacher wanted him to quiet down, he just wanted to give him a task where he's busy for quite a while. And so he asked him to add the first 100 natural numbers, so 1 plus 2 plus 3 and so on. And apparently Gauss was done after a very, very short amount of time, only very few, very shortly, and then named the correct result, but apparently the teacher thought he was just making things up and slapped him basically, as far as the story goes. But Gauss then developed the scheme. He saw the system behind this and saw how this equation can be done. I'll say about this in a second. So the idea is now if we add the first n natural numbers, which we can write in this new notation as the sum of over I from 1 to n of I is 1 gives 1, I is 2 gives 2, and so on. And this is the same as n times n plus 1 over 2. And the way Gauss saw this, of course he didn't write this in this fancy way, but the idea is now if we have 1 plus 2 plus and so on, plus 99 plus 100, and then add these things up again, but the other way around, namely 100 plus 99 plus until we reach 2, until we reach 1. Then we can see, if we add up these two numbers that are standing in each column, they are always 101. So this means we always have 101 in each column, and we have 100 of these columns. So it's 100 times 101. But of course, we sum up twice the same thing, so we have to divide by 2 again. So this means this becomes 100 times 101 divided by 2 because it's here twice. So this is the special case of this formula for n equal to 100. But this is kind of the idea that the young Gauss apparently, or supposedly have. I don't know how much the story is true. Of course, it's really unverifiable, but yeah, this is the way you can see the system behind this. And we now want to prove this equation formally by induction. So by induction over n. Okay, we start with the base case. N equal to 1. So, if we write things down, the sum from I equal to 1 until 1 over I, there's just one summand in this sum. This is simply 1, nothing more than that. But 1 is also the same as 1 times 2 over 2. Which is the other side of the theorem, so which is the right-hand side of the inequality we want to show. So this theorem holds for n equal to 1. Okay, that was very simple. Now the induction step. So, and just schematically we can write this like this. We want to assume that something holds for n and want to prove it for n equal to n plus 1. So we assume that this equation sum from I equal to 1 to n over I is equal to n times n plus 1 over 2 holds for sum n. And then we want to show the thing for n plus 1. And how does this look like? What does this look like? We take the sum from 1 to n plus 1 over I. So we add n plus 1 as well, and then need to replace n by n plus 1 in this theorem as well, so in this right-hand side as well. So this should be n plus 1 times n plus 1, which is of course n plus 2, over 2. So this is the equation we need to show, and let me just erase the blackboard. Okay, we want to now show the claim, and this is now going via a nice little computation. Namely the following. We consider the sum on the left-hand side of the thing we want to show. The sum sum over I from I equal to 1 to n. To n plus 1. Now the idea is if we take out the last of these summands, so the summand n plus 1, we get the previous sum that was on the left-hand side of the induction hypothesis. Namely, this is the same as the sum from I equal to 1 to n over I, plus adding kind of manually this additional summand n plus 1. Okay, but now we have the induction hypothesis, because this is the left-hand side of the hypothesis, and so now we can replace this by the right-hand side of the hypothesis. So, and this is always important in the induction proof. You always need to kind of mark the point where you use your induction hypothesis. This always has to be clear, otherwise you will get some points, reduced number of points, because this is kind of really crucial part of the proof. You always need to make clear where you use this argument. So the induction hypothesis said that this sum is the same as n times n plus 1 over 2 plus n plus 1. This is so you carry this on. So this is only something we need to reformulate, namely if we consider this, so we get, if we bring this onto the same denominator, we get n times n plus 1 plus 2 n plus 1 over 2. And now we just need to see what's happening here. So this is n squared plus n. Here we have 2n and we have 2. So in total, this gives us n squared plus 3n plus 2 over 2. And then one easily checks that this term here in the numerator is the same as n plus 1 times n plus 2 over 2. And this is, of course, the same as n plus 1 times n plus 1 plus 1 over 2. And this is the right-hand side of the claim we needed to show. And so this shows the proof. So this is precisely what we wanted to show. This completes the proof. So we have checked that young Carl Friedrich Gauss was correct in his idea. This completes the proof. Oops. Okay, as another example of induction, there's another important inequality which doesn't look as beautiful as the one of Gauss or as the result of Gauss before, but which turns out to be very useful later on for certain estimates. And this is Bernoulli's inequality. Namely, we take some real number x, which is at least minus 1, and a natural number n. Then the following holds. 1 plus x to the power of n is bigger than or equal to 1 plus n times x. And this we will again show by induction. So proof by induction over n. The base case. N equal to 1. So there's not that much to show. If we have the situation, we have 1 plus x to the power of 1. Yeah, okay, this is just 1 plus x itself, okay? And this we can write as 1 plus 1 times x, which is the right-hand side of the inequality we want to show. So there is equality between those two, so especially there's inequality. So it works. We've checked this. The induction step. So this again, we go from n to n plus 1, just as a reminder. So assuming that 1 plus x to the power of n is bigger than or equal to 1 plus nx, we want to show the claim for n plus 1. We want to show that 1 plus x to the n plus 1 is bigger than or equal to 1 plus n plus 1 times x. So this is what we need to show. Okay, the idea is again, of course, to induce the induction hypothesis, and we need to kind of figure out a way how to do this. And this is again another not that hard computation. Oops. Namely, we compute 1 plus x to the power of n plus 1. In the same way as in the previous proof, we decompose the sum by just taking the last summand separately. Here we can kind of write one factor of this product separately. Namely, this is the same as 1 plus x to the power of n times 1 plus x. So here we know that for this thing we have an inequality, and now here's this factor, and here's the important part, that x is at least minus 1, because this means that this is bigger than or equal to 0. So we multiply with something non-negative, and that was part of the ordering axioms here. that then the inequality stays the same. So this is then indeed bigger than or equal to, and here we use the induction hypothesis. Okay, in your solutions you can just write I dot H dot or something like this, but it just needs to be clear where you use your induction hypothesis. Okay, this means that this is bigger than or equal to 1 plus nx times 1 plus x. Okay, and this is now something we can compute, so we just multiply 1 times 1 plus x gives 1 plus x, and then nx times 1 plus x gives nx plus nx squared. This is the same as 1 plus n plus 1 times x plus nx squared. But we know, since this is a square of a real number, this is again non-negative, and multiplying with a natural number doesn't change this, so this is bigger than or equal to 0, which then means we can again estimate this by saying this is bigger than or equal to 1 plus n plus 1 over x. And hooray, this is what we wanted to show. Okay, so we again found a way of writing the left-hand side in such a way that we can directly insert the induction hypothesis and then took it from there and compute it until we get this result here. So yeah, this shows the claim. And so we've shown Bernoulli's inequality. There's one more famous theorem which is very important, which can be proved by induction, but I won't give the proof here since it's very, very lengthy. But nevertheless, I've given a full proof in the lecture notes. So if you're interested in the proof, you can really read up things. The so-called binomial theorem. Theorem 164, the binomial theorem. An extremely important result. Namely, for all A, B in R and natural numbers n, it holds the following. We want to find a nice formula for A plus B in parentheses to the power of n. We know that if n is equal to 2, we had this nice formula that we can directly compute from the distributivity, and then we could maybe use this and compute further to get the same for n equal to 3, and so on and so on. But now we want to find one formula which fits every n. And so it turns out so this means we multiply a plus b with each other, so we will get several powers of a and powers of b. And products of a and b, of course. So it turns out if you sort the terms correctly, you get that this equals precisely the following sum. This time we go from k equal to 0 to n, so we start at the term 0, of a term called n over k, which I will define in a second, a to the k times b to the n minus k. And this is then a natural number. This is just some coefficient. And this has an interesting form using the factorials I introduced before. So this is really called n over k, this coefficient. This is defined, it's not called n over k, that's in German, it's n über k. Sorry, sorry for the confusion. This is called n choose k. So n choose k, which is a bit of a strange name for this. I will explain in a second why this is the case. So this n choose k is defined as n factorial over k factorial times n minus k factorial. This is n choose k. Okay, so this is the case here for each k, and you can really then, of course, this looks a bit weird, but this is something you can compute. You can insert numbers into here and to really compute the formulas, and as mathematicians, we are happy when we compute something, when we can compute something and don't go into detail. So the proof of this is in the lecture notes. Okay, just as a remark, because these coefficients n choose k pop up very often, and this is because of their meaning from combinatorics. The number n choose k is the number of possibilities to pick k different objects out of a set with n elements. So, for example, when you play the lottery, like in the German lottery system, there's this big German lottery which I don't play because the numbers are ridiculously low. You have 49 balls, labeled from 1 to 49, so 49 different numbers, and each week there are 6 balls out of these 49 picked randomly by a machine, and you have to bet your money on a combination of 6 numbers. So the interesting number for this lottery here would be 49 over 6. This would be kind of the number of possibilities you have to pick 6 different balls out of a selection of 49 balls. And these numbers are really then, so generally this is number n over k, and these numbers can become very, very, very big. For example, for this 49 over 6, I've written down the number. Yeah, you've got, so in the German lottery system, where you have to pick 6 numbers out of 49, there are 13,983,816 possibilities. So this shows that playing the lotto is not really recommendable. But this is a general way. So like in general, how many possibilities do you have to pick things out of a set? I won't go into combinatorics in this lecture because there's simply no time for this and it's not too relevant for you now. But this is kind of, and if you do probability theory and stochastics, these coefficients will also pop up everywhere when you can consider kind of probabilities of choosing elements and so on. Okay, so this was about mathematical induction, and so we've now seen this new method of proof, and you will also, so please do the exercises on induction, because this is something you really have to learn by doing it yourself. And this method we will then use frequently from now on, and this will appear all the time in the lecture. So in the next section, to conclude this first chapter, I will introduce complex numbers, which are then an extension of the world of real numbers, and we will see that you don't need to be scared of them because it's also nice to compute with them. See you in the next video.